You know, there's an invisible line out there in space, right between the Earth and the Moon. And if our Moon ever crossed it, well, it would be torn to shreds.
So what is this thing? How on earth could an invisible line have the power to just shatter a massive celestial body that's been orbiting us for billions of years? It all comes down to a very specific distance.
That line is about 9,500 kilometers from the surface of our planet. Now that might sound like a huge distance, but in cosmic terms, it's practically our next-door neighbor. Think about it. The Moon is currently orbiting us from almost 400,000 kilometers away. If it drifted into that 9,500 kilometer zone, it would be facing absolute annihilation.
To really get why this line is so dangerous, we first need to take a step back and think about what's keeping the Moon together right now.
I mean, the reason the Moon is a big, beautiful sphere is because its own gravity is constantly pulling everything, every single rock, every speck of dust, inward, toward its own center. You can think of this self-gravity as the cosmic glue that holds it all together. But what happens when a much stronger gravity enters the picture?
Well, it turns out this invisible line has a name, and it's not some special thing just for the Earth and Moon. Nope, it's a fundamental concept that applies to basically every planet and star across the entire universe.
It's called the Roche limit. And this isn't a physical wall or anything like that. It's a boundary that's defined purely by gravity. Once a smaller body, like a moon, crosses this line, the gravitational forces from the bigger body, in our case the Earth, just become completely, catastrophically overwhelming.
But how exactly does that work? It's not as simple as Earth just pulling on the Moon. The real secret to its destructive power lies in how that gravity works across a big object. It's a basic rule of physics, right? Gravity gets weaker the farther away you are. So that means the side of the Moon that's closer to us gets pulled much more strongly than the far side. It's not one single uniform tug. It's a differential pull. And that little difference is everything. This difference in gravitational pull creates this incredible stretching and squeezing effect. We call these tidal forces. And yeah, you guessed it. These are the exact same forces that cause the tides to rise and fall in our oceans. Just, imagine them amplified to a world-destroying level. So here's the catastrophic chain reaction, step by step. First, Earth's gravity yanks harder on the front of the Moon than the back. This creates a massive stretching force, the tidal force. And eventually, that stretching becomes stronger than the Moon's own gravity, that cosmic glue we talked about. At that point, it's game over. The Moon just comes apart. But what happens to all the pieces? They don't just disappear into thin air. They'd actually create something truly spectacular, and maybe a little familiar.
All that debris from the shattered Moon would get pulled into orbit, spreading out over time to form a magnificent ring system around our own planet. In fact, a lot of astronomers believe this is precisely how Saturn got its iconic rings. Some ancient moon or maybe a comet got a little too close, crossed Saturn's Roche from it, and was pulverized into the billions of icy particles we see today.
And here's where things get really cool. The Roche limit doesn't just explain how to destroy a moon. It actually tells us something incredibly deep about what gravity itself really is.
We usually think of gravity as a force, right? Something pulling things down. But Einstein showed us something totally different. Mass doesn't create a pull. It actually bends and curves the very fabric of space-time. The classic analogy is a bowling ball on a trampoline. The Moon isn't being pulled by the Earth. It's just rolling along the deep curve that the Earth's mass creates in the trampoline of space-time.
So the Roche limit is basically the point where that curve in space-time becomes dangerously steep. The front of the Moon starts falling down that super steep slope so much faster than the back of the Moon that it just can't handle the strain. It's literally torn apart by the shape of space itself.
Now, if you take this idea to its most mind-bending, absolute extreme, you get a wonderfully weird phenomenon called spaghettification. This is what scientists think happens when something gets too close to a black hole, where the curvature of space-time is almost infinitely steep.
And really, it's the exact same principle as the Roche limit, just turned up to 11. The gravitational difference between the near side and the far side of an object becomes so immense that anything, a star, a planet, even a person, would be stretched vertically and squeezed horizontally until it was torn into a long, thin noodle of atoms.
So, what does this all mean? Whether we're talking about our Moon being torn into rings or a star being turned into spaghetti, everything in the universe has to play by a set of unbreakable rules. It points to a really powerful idea.
Maybe the most dominant things in the cosmos aren't raw forces, but the fundamental constraints, the laws of physics, that dictate what can and cannot happen.
The Roche limit isn't a wall or a barrier. It's a rule. It's a boundary that's defined not by some mysterious force, but by the very geometry of the universe. And it really makes you wonder, doesn't it, what other invisible lines and ultimate rules are out there, quietly shaping everything we see.